Hi, I'm David Herr, and this is my Physics 2022-12 Lab 2 magnetic field of a bar magnet. I will first introduce some key ideas, relevant formula, and go over my setup. I'll then show you my experimental data, calculations, data processing, and observations. After that, I'll introduce my computational model and take a look at my program's output. Finally, I will take a look at the results and answer some questions about the lab. First, for the key ideas in the lab, you need to understand that a bar magnet is a magnetic dipole and will be treated as such in this lab. You therefore need to know the magnetic field of a magnetic dipole on its axis, as well as know that magnetic fields can be superposed. This will be important as we will correct certain results by removing the interference from the Earth's magnetic field. Another key idea in this lab is computational modeling and writing code to visualize a magnetic field. Lastly, we will need to know how to linearize data for this lab. Oh, the formulas relevant to this lab are shown below. The first two formulas describe the magnitude of the magnetic field due to a magnetic dipole, something which will be important in calculating mu, the magnetic dipole moment of the bar magnet. The third equation has to do with the linearization of our data and will be applied in this lab. The loss equation defines approximately the magnetic field of a dipole at any location, which is something we will use in the computational model. Here's a look at the setup on the left. On the left, we essentially measured the distance for different bx's and plotted this data as we will see in just a moment. On the right, we found the perpendicular distance needed for the magnitude of the magnetic field to be 100 microteslas, and then calculated the net magnetic field at the location and showed in the diagram, which will later be compared to the results from the computational model. So here's a look at my experimental data, where I have my raw data as well as my graph of ln(bx) versus ln(r). At the bottom, I have my net magnetic field at a location of 45 degrees off axis from the dipole. Now let's use this data to perform some calculations. So here I have set the first two equations shown to the left equal to each other in order to find a symbolic solution for mu circled to the right. I did pull data from my graph as shown in these calculations. Specifically, n is the slope of the graph of ln k as its y-intercept. I got negative 2.95 for n, and k's value is shown on the left. Using these numbers, I sold from you and got I told you I got 3.206 Newton meters per Tesla. Of the observations shown here, only the first and fourth statements here it is, my bad. Of the first shown here, only the first and fourth statements describe what I observed in my experiment. I noticed that when the magnetometer was far away from the magnet, Bx was close to zero, and that when it was brought closer, Bx increased as expected. So now moving on to my computational model, the first thing I did was define a function for calculating the magnetic field due to a dipole with the given magnetic dipole moment and the specified observed location. I used the formula I mentioned earlier shown here again for reference. I then set the locations for 6 of the 7 points where I'd be visualizing the magnetic field, and 2 of these points are on the dipole axis, while the other 4 are on the perpendicular to the dipole axis. After that, I drew arrows for each of the 6 points as shown in this code here. And lastly, I did the same but for an observation angle at a 45 degree angle of off axis from the dipole axis. So here's the final result, which shows the two on axis magnetic fields in orange, the 4 perpendicular magnetic fields in light blue, and the 145 degree off axis magnetic field in purple. You note that the arrows are scaled proportionally to the magnitude, scaled proportionally to the magnitude of the magnetic field they represent. Here's the text output. What we're most interested in is the second to last line, which shows the magnitude of the magnetic field at the 45 degree off axis position. Let's compare that value to the value found through direct measurement, which is bolded in the table to the left. As we can see, the two values are not exactly the same. However, given the various uncertainties and errors in measurement, the fact that they are in the same order, in other words, means that our results are fairly successful. However, we must also acknowledge that there is room for further improvement in the method which would allow us to obtain more accurate and precise data and achieve a result that is closer. Finally, to answer the questions below, if we had not compensated for magnetic north and let the meter stick at any immediate angle, our results for Bx would have all been off by a specific amount due to interference by the Earth's magnetic field. Not only this, but since the magnetic field superposed, this would have adversely affected the magnitude of the magnetic field in the second part, leading to inaccurate results. If we had to stick the magnets together, I would expect the measurements to all be multiplied by some scalar constant. In other words, I would expect more or less the same result, but with different numbers, as everything included, including the orientation of the magnet and the relative positions, would be the same, and only the real difference would be the magnitude dipole moment. This would just be like if we had replaced our magnet with a stronger magnet and repeated the experiment. Thank you.